Hello, my name is Ryan McKee, and this is Lab 3, Magnetic Fields. The purpose of this lab was to study the magnetic field of a dipole. I then determined the value of the magnetic moment. Finally, I coded a model of the magnetic field around the magnet. Physical principles in this lab included magnetism and magnetic dipoles. Magnetic dipoles are very similar to electric dipoles. Both of their fields create bean-like shapes. The model used in this lab was off-axis magnetic field approximation, as represented by the equation on the slide. In this lab, I found that the magnet had a dipole of 8.67 times 10 to the negative fifth Tesla times meter squared. The relationship I found between the distance and the magnetic field was B equals Kr to the negative 7.88. The picture shows the visual model created by the code. In this lab, I assumed that the magnet I used had no imperfections. I also assumed that no outside electric fields interfered with the results. This was reasonable because the magnetic field of the surroundings was similar to Earth's magnetic field in the region. Finally, I assumed that the models and approximations I used were accurate for my calculations. This was reasonable because I used them within the limits of their intended approximation. This experiment consisted of 3 parts. First, I found the magnetometer on my phone. This made later measurements more accurate. In this experiment, the system was the magnetometer in my phone, the surroundings was everything else, including the magnet, and the initial condition was the phone unaffected by any magnetic fields except the Earth's. Then I found the magnetic field at different locations on the x-axis and studied the relationship between distance and magnetic field on the axis of the magnetic dipole. To do this, I found the distance where the magnetic field was at specific strengths. The system, surroundings, and initial condition of this experiment were the same as the first experiment. Finally, I found the magnetic field off-axis where the net field was 100 microteslas. This allowed me to study the relationship between the computational model and the data I measured. The system, surroundings, and initial condition of this experiment were the same as the first 2 as well. This screenshot shows the data I collected for the second and third parts of the experiment. In this experiment, I found the dipole moment using the y-intercept of the line of best fit of the data, or natural log of k. This gave me a dipole moment of 8.67 times 10 to the negative fifth Tesla times meters squared. The slope of this line of best fit showed the relationship between the distance from the magnet and the strength of the magnetic field. I found the relationship was the magnetic field is proportional to the distance to the negative 7.88 power. This lab also included a coding portion. I was provided with starter code, so I added my experimental results in and made minor changes to find the magnetic field of the dipole at different points. This code also created a visual model of the magnetic field. This photo shows the visual model created by my code. The arrows show the magnetic field surrounding the magnet. The orange arrow shows on-axis, while the cyan arrow shows perpendicular. A pink arrow would show the 45-degree position, but my computational model showed no magnetic field at the off-axis location, which was 0.189 meters x, 0.189 meters y. The code shown shows the function for finding the strength of the magnetic field at different locations. There are significant differences between the created model and the real world. In the model, I assume that no outside electric fields act on my system, which is impossible to completely prevent in real life. The model also only estimated the real-life magnetic field, meaning that the numbers are slightly inaccurate. However, both the model and the real world focused on the same things, so the numbers should come out very similar. This was not reflected in my 45-degree field, which was calculated to be very different from the field that I measured. The computational model showed no magnetic field. I believe this could be due to external magnetic fields in the area causing discrepancies in the results. There are multiple potential sources of error in this experiment. For one, inaccurate distance measurements could have introduced error into the relationship between the distance and the strength of the magnetic field. External magnetic fields could have affected the results for the strength of the magnetic field, introducing error. Finally, the ruler may not have been perfectly aligned with magnetic north. This means that Earth's magnetic field could have caused errors in the results. What if I hadn't compensated for magnetic north? If I hadn't compensated for magnetic north, then the on-axis magnetic field wouldn't be perpendicular to Earth's magnetic field. Compensating allowed the Earth's magnetic field to be on the y-axis, so I could only focus on the x-axis being from the on-axis magnetic field. Not compensating meant that the x-axis would have included aspects of Earth's magnetic field, potentially skewing the results. If I stuck 2 magnets end to end, they would be creating similar magnetic fields. This means the fields would build on each other and create a net field that was almost double. This means the measured distances for each magnetic field strength would be much further. Thank you.